Hi, and welcome to this walkthrough for our second practice paper. Like it says on the screen, please make sure you've had a go at the paper first under full exam conditions, and then without looking at the mark scheme, gone through it using your own notes. The reason we say this is because it's really important that you start to get a feel for the type of thinking that's required at these harder style exam questions, instead of going straight for a walkthrough, which will not be quite as useful if you haven't had to think about it first. Because what the walkthrough is designed to do is to try and help you develop your skills in the exam. But that will only happen if you've had a go at it yourself and really tried to push yourself a second time to see if you can do it with your textbook as well. So in other words, for maximum benefit, you need to make sure you've thought the questions through first, because that will help develop your independence as a student, and it will also help you to develop your resilience as a person taking an exam, sitting there under pressure for the 1.5 hours to actually have to deliver there and then, instead of feeling panicky or worried or your mind going blank. So like I say, make sure you've tried the paper first, make sure you've gone and checked it using your textbook afterwards, then gone to the mark scheme. So several stages should have happened before you're sitting here now listening to this video clip. So this video clip should be really about just clearing up the final few questions that you literally were not able to work through yourself. So the next stage after this clip, if there's still any things to do, it would be go to a subject extension or go and see a teacher. Okay, so let's start with the multiple choice section. And I'm just going to move the page up a little bit. And it says, which molecule is non-polar? So what I'm going to do as we go through this clip is I'm going to highlight, like this, any areas of the question which give you the main clue as to what to do. So the answer actually happens to be A, and then I'm going to go through the reasons for that to help explain it. So let's look at the wrong answers first. In other words, why are they the wrong answers? So with hydrogen sulfide, the blue arrows show the direction of the dipole. So the sulfur is more electronegative than hydrogen. And because of the way in which the dipoles act, the direction they're acting in, they don't cancel each other out. So the larger blue arrow shows that the dipole is pointing in one direction, so that's a polar molecule. And as you can see from the question, they wanted the molecule to be non-polar. So now we've eliminated H2S, let's look at PF3. Now, in spite of the fact that phosphorus has a lone pair, the fluorine is more electronegative than phosphorus, so the bond is polar. The dipole acts in the direction of the fluorine because the fluorine will draw the bonded electrons on the covalent bonds towards itself. So that means that this time the polarity of the molecule acts from top to bottom, as you can see from the larger arrow. But the key thing here, which we're looking at, is that the bonds don't cancel out. You'll see that I've said this a second time now. So now we can actually eliminate PF3. So it's a similar story here, isn't it? You can obviously work out what's going on for yourself. I don't need to take you through it in the same way. So the key thing is that once more, the dipoles do not cancel. So in all three of these cases, the molecule is polar. So let's look at what the correct answer is. So what I'd like you to do is to actually pause the video and have a think about why this is actually the correct answer. So think about the things we've been through over the last few minutes. Think about why we decided that the other molecules were polar. Why is this molecule non-polar? Because obviously the question tells you, we now know that it is, but why is it non-polar? Because it's important to know why you're now choosing this right answer, not just because the others are wrong, but why is this right? So pause the video, grab a piece of paper, and see if you can actually copy this down and then decide for yourself why the molecule is non-polar. Because there's obviously dipoles present, and you can see that for yourself. Why is it non-polar? So come back in a minute or so, and we'll see if we agree. So hopefully we came up with the same idea. So the dipoles act in opposite directions to each other in all three dimensions, up, down, out of the page, back into the page, etc., etc. So the molecule is nonpolar because the dipoles cancel each other out. Okay, so let's move on to the next one. So it says, which equation represents a redox reaction? So let's highlight the bit that's most important. So you could go and do the oxidation numbers for all of the reactants and products, and that would be taking quite a lot of time. Here's a handy hint. So if you've got uncombined elements anywhere in the equation, you can be sure that it's going to be a redox reaction, like that. So there's no uncombined elements anywhere in B, in C, or in D. So because the question isn't actually asking you to use oxidation numbers to prove that it's a redox reaction, that's where you would have to actually write down the oxidation states. Let's look at this one and then just prove what I've just said. So if you take those two to be 0, the hydrogen is +1, the chlorine would be -1, magnesium, being in group 2, would be +2. So what we're looking at is magnesium going from 0 to +2, and the hydrogen going from +1 to 0. So we've got a reduction of hydrogen, and we also have a oxidation of magnesium. So let's now move the page down a bit to question 3. So the next part is about trend in the periodic table, and it asks you which trend is correct. So what you've got to do is to look at each example and think, what does each mean? So if you classify each of your answers as to what's actually happening, are you going across a period or are you going down a group, then you need to think to yourself what actually happens to things like melting or boiling point, and what actually happens to first ionization energy. So the answer to this is actually C, so let's now try and work out why that actually is. So let's look at the first one. If the first one is saying melting point decreases, is it saying it decreases across a period? No. Why is that? Because as you go across a period, proton number increases. So that tells us why this is wrong. Now, if the proton number increases, on face value, you would expect that the first ionization energy would increase. So I'm now looking at D. But that's also across a period, so the same thing would apply. But be careful here, Because if you think of the electron structure of nitrogen and the electron structure of oxygen, you may remember that there's actually a slight dip. So if we look at the two electron configurations of nitrogen, it explains why oxygen actually has a lower first ionization energy. So that would mean that saying that it increases is also wrong. Now, as we know, down a group, the size of the atom gets bigger. But in the case of halogens, fluorine to iodine, as the atom gets bigger, what takes place is you get more electrons. And if you get more electrons, you get more London forces. So therefore, more London forces would cause the boiling point to increase. So for that reason, that one is also wrong. So that means that we can eliminate this one, this one, this one, leaving C as our correct answer. So the next one is quite straightforward. What we do here is we just look at the values in grams and ask what they want of us. They want the empirical formula. To get the empirical formula, what you have to do is get the percentage by mass of each element over its atomic mass. Now, a slight sting in the tail here is they've given us the values in grams. So what we've got to do is this. So to convert the masses into percentages, that's what you'd have to do. So the total mass can be worked out by adding all the values together. So then what you've got to do is take each individual mass. So for carbon, so you can see that the total of all the individual masses adds up to 3.632 grams. So that's going to be the total mass of my sample. So what we do is we divide the individual grams for each element by that total, then multiplying each one by 100, that gives you an individual percentage for each element. So now what we're able to do is divide the percentage by mass of each element by its atomic mass. So now we have these numbers here as our ratio. So what you do is divide by the smallest. So that now gives us, as our correct answer, CH4N, which is why the mark scheme says answer C. Okay, so let's move on to question number 5. So to do this one, which is asking us for the greatest number of atoms, you work out the number of moles and you multiply it by Avogadro's constant, which I'm sure you will remember is the number of particles in 1 mole. So what we've got to do is work out the number of moles in each case. So the thing to do there is moles equals mass over mR. So I'm not going to work through each one because I want to speed the video up a little bit now. I'm aware that we've done 4 questions and it's taken 13 minutes, but I wanted to get you thinking about the individual step-by-step processes first of all and then demonstrate them. So if you were to pause and do that, you can then come to the conclusion that it's going to be A. So I'll put in A as the correct answer as it says in the mark scheme. So moving the page down a little bit, key thing to do here is to look at the data you're given. It's formation data. So there's 2 possible ways of doing this. You can either do it using a Hess's law cycle, which is what I've taught my groups to do, or you can do it using a subtraction. I'm going to pause and pop both down with the workings so you can see how you actually end up with the same answer, which actually happens to be A. Oops. Right, there you go, that's better. So you can see two methods for getting to minus 630 kilojoules per mole. You can either do a Hess's law cycle, or you can do the subtraction method. So the total of the enthalpy of formation of products take away the total of the enthalpy of formation of reactants will end up with the same thing. If you're not sure, try it out and see where it gets you. So let's now move the page down a bit. And look at the next one. So that asks us the volume of oxygen gas at room temperature and pressure is required for complete combustion of that particular amount, 1.25 times 10 to the minus 3 moles of propan-1-ol. The first thing to do is the equation. So it's fairly simple working. What you do, you start with the equation like I said. And you go to the mole ratio of your propan-1-ol to your oxygen. Knowing that 1 mole of any gas occupies 24,000 centimetres cubed, you then work out the number of moles that are required. So we know that there's 1.25 times 10 to the minus 3 moles present. Of propan-1-ol. So to get the oxygen that would react with this, you multiply it by 4.5, giving you 5.625 times 10 to the minus 3. So the volume of O2 required is 24,000 times that amount, which gives you 135 centimetres to the centimetres cubed, which is your answer, C. So now let's move on to the final part. So what we've got to look at here is which alcohol will not react with potassium dichromate. So we're looking for a tertiary alcohol. So what I think the best thing to do is to quickly draw the skeletal formula of each of these so we can work out which one is a tertiary alcohol. So that leaves us with D as our answer. So we're now almost there in terms of at least the multiple choice section. Now if I was to move the page up a little bit, like so, there's a section of a polymer chain is shown below. And what they want is the monomer. In other words, that's the alkene. So to do that, what we've got to do is identify what the carbon chain is of that alkene. So we know that we have 3 carbons. So what that allows us to do is to eliminate these 2. So we can cross those out. Now that leaves us with possibly propene or possibly methylpropene, because we know that an alkene with 3 carbons in it is going to be called propene, or at least 3 carbons in the main chain. But if we look at methylpropene and we look at the actual repeating unit that we get, it's not going to be quite the same as the repeating unit that's actually in the question. So therefore, that particular answer is also out the window. So that means our answer is actually D. So here, it says, which of the following would result in a titer that is larger than it should be? So what does that mean? So the correct answer for this one is actually D. So let's try and go through each individual error and try and work out why it is the correct or incorrect answer. So D says only one. What will be the consequences of completely filling the volumetric flask rather than to the graduation line? So let's now look at the error number 2. So if we're looking at the conical flask is washed out with water before carrying out each titration, if you remember that what's actually put into the conical flask is the solution of unknown concentration. The standard solution goes in the burette. So you put a set amount, such as 25 centimeters cubed, of a solution of unknown concentration, which is what you're trying to find out the concentration of. That goes into your conical flask. So if you wash the conical flask out with water, it doesn't matter, because what's happening is after that you will then transfer your 25 centimeters cubed of your solution of unknown concentration into it. So the extra water sloshing around will have no effect on the number of number of moles. So that means that one is not one of our options. Let's now do the next one, where it says the pipette with which you transfer the solution of unknown concentration is washed out with water before carrying out each titration. So that would give us a smaller titer, and that's not what the question wants us to look for. We want to find something that would give a larger titer. So therefore, this one as well is not one of our answers. So that means that only D is the answer. And while we're at this, it's interesting to note that the way I've said error 2, if that has no effect, then it's not an error. So we need to really just say procedure 2. So now we're ready to go on to the longer answer section, starting at question 11. So this one tells us that carbon monoxide can be made in the laboratory by heating a mixture of zinc metal and calcium carbonate. So it gives an equation, and it says it's a redox reaction. So it asks you to deduce which element has been oxidized and which has been reduced, and state the change in oxidation number in each case. And they give you the spaces in which to do that. So the easy thing to do is to assign oxidation numbers. So you can see quite clearly that zinc goes from 0 to +2, so it's an oxidation. And the carbon, sorry to make a slight correction there, carbon goes from +4 to +2, so that's a reduction. So now we can decide what to write in the spaces below. Okay, so the next thing we've got to do is to draw a dot and cross diagram. Show the outer electron pairs. And I'm going to place an emphasis on pairs in a molecule of carbon monoxide. So we know that it contains a triple bond, and this includes a dative covalent bond. So there's a couple of things we can think about this. So the dative covalent bond and the triple bond actually give us clues. Now let's try and put this together. Obviously what we've got to do is have the outer electron pairs, and we'll put carbon on the left and we'll put oxygen on the right. So carbon has 4 electrons of its own, oxygen has 6 electrons of its own. So this is the criteria we have to meet. Carbon must have 4 electrons of its own, oxygen must have 6 electrons of its own, and both must end up with 8 electrons in their outer shells. So in that mix, we've got a dative covalent bond. So let's think about which atom has more electrons to share. It's oxygen, because oxygen has 6. So it's highly likely that it's going to be the oxygen that has a dative covalent bond. Like that. Now it's a triple bond, so it has 3 electron pairs, that's one of them. Another electron pair, and another electron pair. Notice that I'm alternating the dots and the crosses. So the carbon is what has the crosses. 2 of them have been used up already, so we can put that there. Carbon now has 8 electrons in its outer shell. So carbon's been sorted out. The oxygen has 6 electrons in its outer shell. We've used up 4 of them, so we now put 2 there. So oxygen has 8 electrons in its outer shell. So that gets that question done, or at least that page. There is now part C to go on to. So let's do some question reading here, because we've got to be quite careful, because this is partly practical skills and partly deduction, because it might not be a practical that you've done. So the reaction of zinc and calcium carbonate. So what does that tell us already? Then it says the student measured the volume of gas produced. So that's obviously with this apparatus here. So, it doesn't say what gas is produced. It would be easy to assume that it's carbon dioxide. That's what you think when you heat a carbonate, surely. Let's just have a look at the question before we jump in and then decide. So moving the question down, they've been a bit cheeky and they've put carbon monoxide down here. So that means carbon monoxide is going to be the product, not carbon dioxide. And while we're at it, it's in centimetres cubed. So we can go back down to what we've got up here and add to it. So if we've been told what things we have by the question, surely that means that we can deduce these two by difference. Okay, so the mixture contained 0.27 grams of powdered zinc and 0.38 grams of powdered CaCO3. First thing I would think if I saw that is there's going to mean some moles equals mass over atomic mass somewhere. So what it tells us to do is calculate the maximum volume of carbon monoxide. Not just the volume of carbon monoxide, the maximum volume of carbon monoxide, showing all our working. So what the maximum volume of carbon monoxide means is until one of the reactants is used up. So that will mean automatically that the other one will be in excess. So bear that in mind when we're doing our calculation. So if we work out the moles of each element, you can see that one of them is in excess slightly, the zinc, because it has a bigger number of moles, but only just. So that means that the determining factor, the limiting factor, what will actually determine the number of moles of carbon monoxide, which is what we need to work out the volume, is the number of moles of calcium. So what we can now deduce is that you've got 0.038 moles of carbon monoxide. So now what we've established is that the number of moles of carbon monoxide we're trying to work to is 0.038. So that's the maximum moles that you can get from that particular mixture with those particular amounts. So now let's get stuck into how to convert that into a volume. So as we looked at earlier, the volume is in centimetres cubed, isn't it? If you look at the bottom of the screen, you can see it's in centimetres cubed. So that means that the volume is 24,000 times the moles, because there's 24,000 centimetres cubed of gas in every mole, and that applies to any gas. So we now have worked it out that it's 91.2 centimetres cubed. That's the calculator value. However, if we look closely at the values we're given up here, 0.27, 0.38, they're two significant figures. So always in these types of calculations, take a hint from the number of significant figures that the question is giving you. If it doesn't necessarily give you an instruction as to how many significant figures, look at the question itself. And failing that, go for 3. So 0.27 is two significant figures, 0.38 is two significant figures, so 91.2 to two significant figures is 91. Okay, so we need to move the page up a little bit to look at the next part of the question. So it says the student did not obtain the volume of gas predicted. So apart from further repeats, so in other words, don't default to just repeating it to get an average, suggest 2 improvements to the practical procedure that will allow the student to obtain a more accurate result. So let's have a look at this. Let's have another little read of the question. If we bring the question down again, the maximum volume of carbon monoxide measured at room temperature there we go. If it's been measured at room temperature, but you've been heating it, then surely you need to let it cool down so that the volume of the gas that you collect when it's hot is allowed to contract slightly as it cools down to room temperature. So that would be improvement number 1. Now, it didn't say for how long they heated it. And if you heat it once, it didn't say whether they'd measured the volume when it was still moving, as in whether the gas cylinder was still moving. So secondly, wait until the syringe has stopped moving, so you know the maximum amount of gas that you've been making has been produced, and the reaction is complete. Okay, so let's now go to the next question. So we're over the page onto part D. Let's move the page up a little bit. So it says the student repeated the experiment in C using different quantities of zinc and calcium carbonate. The student measured the total volume of gas collected over time. So obviously the improvements have been put into place. And the student's results are shown below. So what does it ask you to do? It asks you to plot a graph from the data provided and to include a line of best fit. So it's all good practice that you've been doing at GCSE, it's just transferring it over. So I'm going to put some tips down on how to approach this up here. There's a few hints and tips there. For scaling, use as much of the provided graph grid as possible. In other words, don't do a graph there and expect to get marks for it. The time is the x-axis, volume of gas is the y-axis, because the way that the data is presented, you read from left to right, like so. The axes must be labelled including units. I cannot stress this enough. Please put the units in. So time on the x-axis, and then in brackets seconds. On the y-axis, total volume of gas collected, in brackets centimetre cubed. Line of best fit could be a curve or a straight line depending on where the points fall. So the next screen is going to be my version of this, but done in pen and scanned and pulled onto this video clip via my cloud storage. So it's not really me drawing it here, because it's a bit difficult to draw a very, very accurate graph using an iPad pen. So here we've got the same page, but I've obviously drawn on it using my normal coloured pens and bits and pieces. And I've pulled it onto here as a PDF, as you can see. So let's have a look at the graph. Now this is actually an excerpt from my scanned version that I did before I did this video clip. The scanned version is also available on the VLE, so you can upload that and print it off if you want. So basically the walkthrough we're doing at the moment is just the same as the scanned version, but with me talking about it in the background. So you'll see that I've drawn my curve. I've got a line of best fit that happens to have ended up as a curve. So let's show it here. It's my curve of best fit. Notice that there's a point that doesn't fit on the curve of best fit, so I ignore it. That's actually one of the marks, so ignore any anomalies. And the way that I've done my points is I've done them as a dot with a circle around them. You can do crosses if you want, so you could, for example, if you wished, I suppose, do that, or that, so on and so forth. Nothing wrong with doing it like that. I believe that they accept either type. Now, you'll see up here, I haven't come to part II just yet, there's a tangent. So if we now have a look at the next question, it asks you to say, use the graph determining the rate of reaction. So what that means, in other words, is you have to show that you've actually used the graph. Not just that they can take your word for it, what is the actual evidence that you've actually used the graph. So in this one, going back to the graph, you can see that I've actually physically said what is the tangent for part II. So the tangent allows us to work out dy over dx, and that gives us 0.65 centimetres cubed second to the -1 as your rate of reaction. So what you'll need to have here is the next page on your script. In other words, you'll need to have part E, where it asks you to use the graph to determine the rate of reaction after 50 seconds. So at 50 seconds, what I do is I have a line coming up, oops, up like that, a little bit too thick, a line like that coming up, roughly to there. So at this point I draw my tangent. So the tangent has to be a line that sits on the curve and just touches the curve at that point. So that allows us to work out dy over dx. Now dy is going to be that, and dx is going to be this. So you divide one by the other, so that's dy. And that's dx. And that's what allows you to do this, to get this here. Whoops, sorry. On this next one, there's quite a lot of information we're given, so it's worth pausing and just taking a bit of time to have a look through it. So the reaction is taking place between hexane and chlorine. So at this point, I think you've got an alkane being chlorinated. So what type of reaction we're talking about? Free radical. So it tells you exactly what's going on. The chlorine is made, so no surprises there. We've just realised it's a free radical substitution. So the chlorine is made by the reaction of aqueous sodium chlorate. So sodium chlorate 1, you should just pause for a second and think about what sodium chlorate 1 actually means. So if the chlorine is in oxidation state 1, we know that oxygen is going to remain as -2. We know that sodium is always going to be +1 because it's a +1 element. So that allows us to do a quick deduction, like so. So that's -2. That's +1. So adding it all up so that the whole thing is 0, this would have to be -1. Sorry, +1. So two colourless layers, knowing that we've got hexane and we've got aqueous sodium chlorate. So aqueous and hexane, one is going to be polar, one is going to be non-polar, so they're going to separate out and not mix. And we also know by looking at the procedure, hexane is mixed with 1 centimetre dilute aqueous sodium chlorate 1 in a test tube. So the next one is where the acid is mixed or slowly added to the mixture. So dilute hydrochloric acid is going to be an aqueous solution anyway. We know this from our general knowledge. So the acid mixes with the lower layer, which turns a pale green colour. Now the pale green colour we're talking about, let's actually make it pale green. There we go, how about that, eh? Pale green colour must be chlorine. So it then says that the tube is stoppered and shaken in an attempt to mix the two layers together, or at least to bring them into contact with each other. But what's interesting is the pale green colour then moves to the upper layer, leaving the lower layer colourless. So remember we said that hexane was non-polar. It must mean that the chlorine dissolves more easily in a non-polar solvent because it's a non-polar molecule. So the next thing is the tube is placed under a bright light. So as soon as you see bright light mentioned, and we're talking about halogens and alkanes, that's when the radicals are made. So that's what started to happen. Your chlorine has turned into 2 chlorine radicals. And as you'd expect, because it's no longer Cl2, the pale green colour slowly disappears, leaving 2 colourless layers. So the pale green colour disappearing means that the chlorine radicals have been made and the chlorine, as in Cl2, is no longer there. So let's move the page up a little bit so we can make some room to start doing the rest of the question. Okay, so what we got? The reaction between aqueous sodium chlorate 1, which we know to be NaClO, because we deduced that earlier, and dilute hydrochloric acid, which is aqueous sodium chloride, as well as chlorine. In other words, they're telling you in words what to put into the equation. In other words, that's what we know already. However, it's not balanced because what has to happen is that the hydrogen has to be dealt with somehow. So look carefully at what happens on the right hand side. There's oxygen on the left-hand side, but there's no oxygen on the right-hand side. So that means that hydrogen has to be used up and oxygen has to be used up. Hydrogen, oxygen, maybe water? Like that. So the next thing asks us to outline a simple practical test that could confirm the presence of chloride ions in the lower layer and give the expected result. So in other words, you have to say what you would expect to see. So this one is quite straightforward. If you've done your Group 7 work, it's the silver nitrate test. So just be on the safe side, say physically that you'd shake to mix it up. And the result you'd expect is a white precipitate. You don't necessarily have to say that it's a white precipitate of silver chloride, because it doesn't ask you. It just says give the expected result. And just for reference, when we're talking about precipitates, seeing as we're on the subject, if you just say white solid formed, that's not good enough, unfortunately, because in chemistry, the word precipitate actually means the formation of an insoluble solid from two aqueous ions, which is what's taking place here. So just in case, for future reference, when we're doing work with precipitates, actually use the word precipitate. Don't just say white solid, or it goes milky, or it goes cloudy, or it goes white, or the solution goes white. There's lots and lots of different ways you can get your observation wrong. Stick to the word precipitate. Really important. Then it asks you to name the apparatus that could be used to separate the two liquid layers present. This is one that you would need to be able to do once we've done organic synthesis. So once organic synthesis has been done, then you'll know what I'm talking about here. So if you're listening to this before we've done organic synthesis, then it may be a little bit hazy for you. But if you've done organic synthesis, you'll have come across a piece of equipment called a separating funnel, which is what the answer is here. So by the time you do the actual progression test into your second year, so your end of year exam, so when you do the actual end of year exam, you will have done organic synthesis, obviously, and separating funnel would have been the one that to choose. So let's go to the next page now. And it says the reaction of hexane with chlorine took place when the bright light was switched on. So like we said a few minutes ago, that is actually what would start off the initiation. So in other words, the initiation step would need light to actually provide enough energy for the homolytic fission of the Cl bond. So what we're talking about is obviously the electrons moving onto the individual chlorine atoms. Now this little curly arrow I've put, sometimes called a fish hook for obvious reasons, it's not actually in your specification, but if you were to look up free radical substitution on the open internet, quite often this is used to describe the movement of one electron. But it's not on your spec, so don't worry about suddenly having to go and recall it, because it won't be in the OCR book, so you don't need to worry about it at all. So, it says give the skeletal formula, so it's really important that it's the skeletal formula of one possible organic product of this reaction. So it says one possible organic product. Now, it's going to be a bit difficult for me to put all the different possibilities, because you've got hexane, so that means that you have, at the very least, this. Now the thing is, you could put chlorine onto any of the points on here, so instead of drawing all of the different possibilities, I'll draw one. So you could have one like that, or you could have one like that, and at random one, oops, one coming off there. Sorry, trying to get this absolutely accurate. There you go. So those are examples only. But the key thing is that chlorination could take place anywhere along the hexane chain. So I'm highlighting the carbon atoms where it could occur. And this asks you to say, explain why this type of mechanism is likely to produce a mixture of organic products, and specifically a mixture of organic products. So you could have multiple and further substitution of chlorine for hydrogen atoms or anywhere in hexane until you could actually end up having 14 chlorines and 6 carbons out of 14 hydrogens and 6 carbons. So to be quite honest with you, this bit here is just really for illustrative purposes, so you understand the idea of how many times we get multiple substitutions. You don't really need that in there as well. It's not on the mark scheme, so you don't need to put it in there. But it just illustrates what I'm trying to say. So this is an applied question because it talks about the production of ethanol, which actually isn't in your book. So it's not on the specification, but there's enough information here for you to take stuff you do know and apply it to a new setting. That is a key skill at A level, so it's not designed to completely trip you up, but it's designed to make you stop and think. Expect that at regular intervals in any paper you do. So it's kind of a mindset thing, isn't it? Thinking through what you know and trying to make it fit what's in front of you. Okay, so it says every year 2 million tonnes of ethanol are produced worldwide by the hydration of ethene. I'm just getting the right place in my script, which I prepared. So the hydration of ethene is definitely one that you've done. That is one of the reactions of alkenes that you've done, so that's your way in. Okay, so the reaction is typically carried out using a catalyst at 300 degrees and 6,000 kilopascals, so in other words, high pressure at high temperature. Let's just make a note of that because that will be there for a reason. They haven't printed that for no reason at all, so I'd suggest you need to draw upon that piece of information at some point later on in the question. So it says the catalyst allows the reaction to reach equilibrium more quickly at the given temperature and pressure. So in other words, the temperature and pressure doesn't need to be further altered to allow the catalyst to do its work. So it says state the catalyst, and it's interesting it says the catalyst. So in other words, there's only one really that's in the book that you're expected to know, and that is H3PO4. So then it gets you to outline how a catalyst increases the rate of reaction. So specifically what they want is how it does it. So there's 2 marks on offer, so there's 2 specific things I would say that need to be said. The first thing is that it provides an alternative reaction route which has a lower activation energy. So the consequence of this chemically is that more molecules now have kinetic energy greater than or equal to the activation energy. So you need to follow it up with a chemical consequence for the rate of reaction. Not just that there's a reaction route of lower activation energy, so what does that actually mean in terms of the kinetics of the reaction? So moving to the next page, it says an increasing amount of ethanol is made by the fermentation of glucose from plants rather than by the hydration of ethene. So although you knew about the hydration of ethene and it happened to make an alcohol, what they're introducing in this question is the fact that it's actually used in industrial scale to make alcohol, to make ethanol. And it says an increasing amount, in other words, more and more and more, we're turning to things like glucose from plant matter because it's more sustainable rather than using fossil fuels. But if we're honest, these are ideas that you've come across before at GCSE, probably even before that. So it's been quite a few years we've been covering this with you in science. So just to mention sustainability and renewability is not enough anymore. You now have to think in what way and why is it more sustainable and renewable, given the information that I've actually been given in this question. So it says fermentation is catalyzed by enzymes. So enzymes, as we know, are biological natural catalysts. They're produced in cells of living things from yeast, in this case, at a temperature of 40 degrees C and 100 kilopascals. So a lot lower temperature and a lot lower pressure. So we have to compare the sustainability of each process using atom economy, raw material, and reaction conditions. I'll move it up a little bit. So we've got hydration using ethene from crude oil. Why? Because in the question, I think earlier on in the paper it might have said it actually, on the previous page. I can't go back to the previous screen and I'm recording unfortunately with this particular app, so let's have a quick look and I can ask you to go back onto your script. Yeah, if you go back to the beginning of the question, it said every year 2 million tons of ethanol are produced worldwide by hydration of ethene, obtained from crude oil. So, we're making a link to that now. So fermentation, on the other hand, uses plant-based raw materials, which are renewable because plants grow much more quickly compared to the production of crude oil, which takes millions and millions of years. So it's not really considerable as a renewable resource. So finally, what we're going to talk about is the reaction conditions. There we go. So obviously, ethene consumes a lot of energy to maintain the very high temperature and pressure needed, but that's not needed for fermentation, so fermentation is more sustainable in terms of reaction conditions. So what we've got to now do is weigh up overall, on balance, which of the two is more sustainable. So looking at atom economy, I think hydration wins there, but under raw materials and under reaction conditions, fermentation comes out on top. So on balance, fermentation is the better option in terms of sustainability. So that's what they ask you to do, because obviously up here it says suggest which process is the more sustainable. So on balance, fermentation is the more sustainable of the two processes, like you've just said. So here we've got a large proportion of the world's output of organic chemicals is used to make additional polymers, and they have a variety of uses. So it says polypropene is used to make packaging, textiles and rope, and it gives you a repeat unit for polypropene. So it asks you to talk about it being saturated. So you may think, hang on a sec, we're talking about propene, aren't we? That usually means unsaturated. However, if you've got a polymer obviously what's happening is the carbon-carbon double bond that used to be there has now had all the carbons filled up with hydrogen or other groups. So therefore every single carbon has 4 bonds. So what you need to put is this. So to state the bond angle around each carbon atom, and because you've got 4 bonds around a carbon atom, that's a tetrahedral shape, so the bond angle that goes with that is 109.5. So it's worth pointing out here that you don't need to put tetrahedral because they don't want the shape, they want the bond angle. So let's now move the page up a little bit. So it says, after polymers have been used for packaging, the waste polymers need to be processed to save resources, for example by recycling. So it says describe 2 other ways. So don't go and talk about recycling because they've already given you that in the question. And it has to be processed in a sustainable way, otherwise it's not worth processing to try and get rid of it as waste. So one thing you could do is burn it. I know it sounds a little bit harsh in the sense that it's giving off carbon dioxide, but what you're doing is you're using waste to create energy instead of using fossil fuels. So you could also use it as a chemical starting material, or feedstock as we call it, by undergoing catalytic cracking to make an alkene again. So going over the page, it talks about a substance called polyethanol. I want to pause for a second and draw your attention to the fact it's polyethanol, not polyethanol. So polyethanol would have come from this substance. So it's basically an ethene molecule with a OH group coming off it. So it's a primary alcohol called ethanol instead of ethanol. So one repeat unit of polyethanol, what you would do is take the carbon-carbon double bond and make it into a carbon-carbon single bond, because obviously you have many of them joining up like that. You leave the trailing bonds on the left and the right, and if you look carefully at where the OH group is coming off, that's your carbon chain, that's another carbon chain, etc. It's coming off there, so we need to make sure that we draw it there, like so. It's always a good idea to put the square brackets in. Sometimes in past papers from previous specification it says ignore square brackets and ignore n. I just like to cover myself by putting them in. I mean, it takes half a second, so what's not to like? So now what we can do is move down a bit, and it says analysis of the structural isomer gave the following data. So you've got the infrared spectrum. So obviously what you're going to do in a minute is grab your data sheet and use it, but it's very important that you quote the specific wave numbers that are given in your data sheet, because if you're quoting other wave numbers that are close but not quite the ones that are on your data sheet, you will not get any marks, so it's a waste of your time. So let's have a look at what the information is that we can get from this. There's no OH group, and there is a C double bond O group present. So what we've done is we've established that the structural isomer doesn't have an OH group, even though the ethanol does, but it does have a C double bond O. So I don't know if you're thinking of what I'm thinking. OH group is gone, C double bond O group now in its place. Oxidation of the alcohol to an aldehyde maybe. Well, we'll see. So a possible clue. So let's now look at the next bit of information that we've got, which is the mass spectrum. So we've got several major peaks, we've got 3 big ones, and we can say something about them perhaps. Now because it's a structural isomer, the MR is fairly irrelevant, so don't go down the route of trying to say something about the MR, because all they'll say to you is, well, the original ethanol had the same MR, so that would have the same on its mass spectrum as well. So that would be my advice at this point. So what we need to do is look at the other two. Now one of them has an m over z of 29, another one has an m over z value of 15. So considering you've got a C double bond O group, what could be added to a C double bond O to make 29? Because the C double bond O is 28. So that would obviously be CHO. So those are two possible candidates. So if we now move the page down a little bit so we can start to say something about that. So 4 marks are an offer. Now if you've annotated your mass spectrum already, obviously not writing this lot because that's just advice from me. I'm talking more about the m over z values, etc., and the value of the the density of the peaks, such as that. So this stuff, if you put this stuff down already, you'll probably get credit, even if it's written in that particular part of the page as opposed to down at the bottom. So you need to say something about the infrared as well. You need to try and pull it all together. And it says in your answer, you should identify the structural isomer, and also you should make clear how your explanation is linked to the evidence. So we've annotated our mass spec, we've annotated our infrared. Let's put it together in a couple of sentences. So we pulled together the mass spectrum data and the infrared spectrum data and used it to deduce that we've got ethanol. This next one is about the Haber process, and you can see clearly what we're talking about. Increasing the pressure on the rate of reaction. Now, I'd like to point out at this point that it's on the rate of reaction, and you're probably used to thinking of the Haber process in terms of the equilibrium. So if we're talking about equilibrium, pressure would have a slightly different effect on the equilibrium, and it would shift it one way or another. But it's the rate of reaction they want you to think about. So it's not actually asking you, at this point, anything to do with the equilibrium. So they're being a little bit cheeky by asking you about rate of reaction, but then at the same time in the textbook it says rates and equilibria, so we group the two together. So like we mentioned a moment ago, it's increasing the pressure. So what that does is it crowds the molecules closer together, so there's more collisions in a given unit of time. So because the molecules are closer to each other, they're in greater proximity, they're able to collide more often. So if you look at the way that I've put connectives in the sentence, so increasing the rate, the reason why is because molecules are closer to each other, so the consequence is that there are more collisions per unit time. You need to be thinking about your language so that what you're saying is a statement, followed by a reason, given by a consequence. The next part is it asks you to create a value or calculate a value for Kc for this equilibrium. In other words, for this equilibrium means the one that has these particular values at Kc. So therefore, at equilibrium, those are the concentrations of each of the individual components. Your NH3, your H2, and your N2. So as you probably are aware, you write a Kc expression by doing the products over the reactants. So at this point we might need to move the screen up a little bit to make some room to put our calculation in. So you write the Kc expression and then you put in the numbers, and that should give you 0.0801. So next what they want us to do is to explain how the following changes would affect the amount of NH3 present in the equilibrium mixture. So before we go any further, let's go back up and look at the equation. So looking at the equation, you can see that the delta H value is minus 92, which means it's exothermic. And that on the left-hand side, 4 moles, right-hand side, 2 moles. So let's look at what they're actually asking us. So use of a catalyst, well, in equilibria, all that catalysts do is it enables equilibrium to be reached more quickly by increasing the reaction rate on both sides. But with a higher temperature, because it's an exothermic reaction in the forward direction, in order to offset the effect of the extra heat that's being added, the more endothermic direction will be favoured. So that means the reverse direction will be favoured, which means there will be less NH3. So what we're doing now is moving on to the next question, the next part of this one. It's a calculation. So I have that calculator ready. So it says 1 tonne of ammonia, and they like doing this in A-level questions. First thing you've got to think about is convert tonnes to grams. We've got 1.35 tonnes of urea formed, which is highlighted in the equation, and the mole ratio of ammonia to urea is 2 to 1. So what it's asking for is the percentage yield. So to do percentage yield, you need to do this equation. So it says to show all your working. So to enable us to be able to put some figures into that equation, we've got to work out what the moles of everything actually happen to be. So let's start with ammonia. So what we've done is we've used mass over MR to work out the number of moles of ammonia used, and the expected amount of urea, because it's a 2 to 1 mole ratio, would be half of that, which would be 2.9412. So the expected one is the same as the expected yield. So but in reality we got 1.35 tonnes of urea. So in other words, how much in mass is the expected amount, and how does it compare to the amount we actually got? So what I meant to say is converting the actual mass of the urea, the 1.35 tonnes, into moles. So what I want to do is be able to express this as a percentage of this. So you've got the actual yield of urea at this point now. So we divide one by the other, multiply by 100, to get a percentage yield, and it's 76.5. Right, so in this one, if you look at it, it's obviously a description of an experiment of some kind. It tells us that you're identifying an unknown carbonate, and I can see the word titration in there, so that means that there's some data we're going to be using. So let's have a look. It says the student weighs a sample of the solid carbonate in a weighing bottle, and then they tip the carbonate into a beaker and they weigh the empty weighing bottle. So what this is called is weighing by difference. So I'm just making a mental note to myself of what that means, which is, although not all of the carbonate is in the beaker, which makes it sound like it might be a problem, because they've weighed the empty weighing bottle, they now know exactly how much carbonate they will be reacting, so it's actually not as much of a problem as you might think. Why am I talking about it in terms of whether it's a problem or not? Because it says down here, another student suggests 2 possible sources of error, and he or she said that a small amount of solids remains in the weighing bottle. True, but it doesn't matter, because so long as you know how much solid you're reacting, you're not losing any reacting moles, so you can keep track of your reacting moles and work out your concentration at the end, or your whatever the outcome you're trying to get, in this case identifying an unknown carbonate. So it says that the student prepares a 250 centimeters cubed solution of the carbonate. That's really important to make a note of that, because you'll use it at some point during the question. And the student titrates 25 centimeters cubed of that solution, so in other words 1/10 of the original. So it might be worth just bearing that in mind for later on in the question as well. So if you've got another possible error, a small amount of solution remaining in the beaker, where would that come from? So let's have a look. Part A, the sample of carbonate is dissolved in 100 centimeters cubed approximately, and the solution is transferred. So if you're transferring a solution, you need to make sure all of the solution has been transferred. So you need to bear that in mind as well. So a small amount of solid remained in the weighing bottle. So let's now look at what it asks us to do. It asks us to state whether the other students' statements are correct and how could the procedure be improved, for 2 marks. So you need to look at both statements and make a judgment on each for 1 mark, and then you need to say how the procedure could be improved for the other. So something along those lines is what you need. So statement 1 is false because it's not an error. Because like we've said up here, not all the carbonate is in the beaker, but the mass by difference will mean that the person doing the titration will know exactly how much they will be reacting. In the second statement, a small amount of solution remained in the beaker. The problem with that is that you'll leave some of the solution behind and there will be still some moles of solute, your carbonate, that are not titrated. So in order to make it better, you need to rinse the beaker into the volumetric flask so all the moles of solute are then in one vessel. So the solute is obviously your carbonate. So let's now go to the second part of that question. Where it says that the student carries out a final part of the experiment by adding a specific concentration, in this case 0.1 moles per decimeter cubed of hydrochloric acid to a burette, and performing a titration using the sample of the aqueous carbonate they prepared before. So they weighed the burette to the nearest 0.05 centimeters cubed, and the pictures show the initial and the final burette readings, and they want you to record those readings and the titer. So remember, when you're looking at a burette, if you recall, we use the bottom of the meniscus, don't we? So if we have a look at that, we can see that we have, on the first reading, which is there, we're reading downwards from 0, and in this one here, final reading, we're reading downwards from 0 again. So that means our first one is going to be 0.60. Now remember that it's to the nearest 0.05 centimeters cubed, so 2 significant figures. Sorry, what I meant to say is read to 2 decimal places, but that also means that automatically you're doing it within 0.05. So if you do it within 0.05, the 2 decimal places will fall into the reading that you actually write anyway. So you should end up with something like that. So we need to move the page down slightly to have a look at the next part of the question. So it says, describe what the student should do next in order to obtain reliable results for the titration. So think carefully what this means, what they should do next to obtain reliable results. They've got 1 reading so far, one titration, or one titer, as we call it, I would suggest they need to get another one, and it needs to be close to that titer. So you may remember doing concordant results when you did titrations yourself. So there's two things that need to be done to actually obtain a reliable result. You actually have to do the titration again and repeat it until you get concordant results that are within 0.1 centimetres cubed of each other. The standard concordancy limits for A level are 0.1 centimetre cubed. That's just something you need to know. And obviously once you've got your two concordant results, you can take a mean or an average, and then it gives you something called the average titer. So finally, on that question, let's move it on. The equation below represents the reaction between the carbonate and the hydrochloric acid. And you may recall a few minutes ago I told you to remember that we had 250 centimetres cubed as our stock solution that was made up to in a volumetric flask, and we used 25 centimetres cubed samples of that to titrate, therefore 1/10 of the original solution from which your weighed sample of carbonate was produced. So that's where this comes in, because obviously you can see already that we've got to calculate something. And we've also got a mole ratio in an equation. So no surprises here that we're going to be using the equation, the calculation. Basically it's going to be a mole calculation using our results. So it says calculate the amounts in mole of the M2CO3 used in the titration. So what do we know from the titration? We know the number of moles of HCl, because that's what we were titrating. So the HCl was our standard solution. What a standard solution is basically something that you know the concentration of, that you also know will react with something else, and that something else, in this case your carbonate, is what you don't know the concentration of. But what we're trying to do is actually work out the identity of the carbonate. So to do that we have to go via MR. To work out the MR we need to get the moles. Then we can use the moles and the mass from the beginning of the experiment. Okay? So first part, calculate the amount in moles of M2CO3 used in the titration. So using moles equals volume times concentration, that gives us 0.00222. And if we look at the mole ratio in the equation, we can see that it's 1:2 between the carbonate and the acid. We've just worked out just now the number of moles of HCl, so therefore the number of moles of carbonate is half of that. So then it says the student's mass readings are recorded below. So you get the mass of your weighing bottle and the carbonate together. Sorry, I just want to re-highlight that in a slightly different colour, just to avoid confusion. There we go, that's my highlighting colour. And the mass of the weighing bottle in grams, so the difference between them is going to be the mass of the carbonate. So we need to work out the mass of the carbonate used. So we work out the mass of carbonate, and then before we go into the moles and mass calculation, we have to remember, like I mentioned a couple of times during the course of this clip, that in this question we had a 25 centimetre cube sample of an original 250 centimetre cube stock sample that was made up. So if you notice, your original 0.00111 moles of carbonate we worked out in part I has now been multiplied by 10 to make 0.0111. So now we can start to work out the MR of the carbonate, because we have the mass and we have the moles. So I'm going to need to move the page down slightly, obviously, so I can show you how to do this. So shifting the page up, there we go. We need to know that MR for carbonate is going to be mass over moles, which gives us 142.3 grams per mole. Now, how do we work out the identity of the carbonate from that? It's not as difficult as it might look. So let's write down the equation that we know for the carbonate, the formula. So we know that the whole thing is 142 grams per mole to the minus 1, sorry, once minus 1. What we don't know is what's the carbonate, what's M. We do know that's 12. We do know that that's 3 times 16. So we can add those up to give us 60. So we know that carbonate, i.e. CO32 minus, that's going to account for 60 out of our 142.3. Just put 0.3 here. So therefore, it's quite straightforward from here. The M2 part is going to be 142.3 minus 60 equals 82.3. And because there are two of the metals, M, the AR of the metal that you're after, whatever it happens to be, is going to be 82.3 over 2. That gives us 41.15. So that means the metal is potassium. So therefore our carbonate is potassium carbonate. Okay, so let's go on to the next bit. It's actually the last part of the paper, so we're nearly there. And it says alcohol A contains carbon, hydrogen and oxygen only. So if we highlight our alcohol and what it contains, so it says it can easily be vaporized. That's a little hint. Don't need to say that to you, but if you think about it, that must mean that the carbon chain is quite short, so there are relatively few intermolecular forces. So then it says that 1.15 grams of this substance, this alcohol, produces 761 centimeter cubed of gas when vaporized, measured at 100 kilopascals and 366 Kelvin. We've just been given 3 pieces of data, all of which feed into PV equals nRT. So now we know what calculation we'll have to do. And the outcome that we're trying to get is the molar mass of compound A. So if we think about how PV equals nRT relates to the molar mass of compound A, it's via moles, isn't it? So now what we can do is we can rearrange PV equals nRT so that N is the subject. So making sure we've converted our units from the ones that were given to us, that now gives us 100,000 times 7.16 times 10 to the minus 6 over 8.314 times 366, remembering that R is 8.314, but that can be from the data sheet. So dividing all that through gives us 0.0250 moles. But we're not quite there yet because we want the molar mass. So to convert the moles to molar mass, it's very straightforward. So remembering that MR is mass over moles, that gives us 1.15 over 0.0250, and that gives us 46.0 as our molar mass. So what we've got to do is deduce a structure for A. Now we know that it's an alcohol, so we know it's got an OH group somewhere. So the OH group accounts for 17 out of that 46. So the alkyl chain, the remaining carbon and hydrogens, are going to be 46 minus 17 equals 29. So the way you can do this is to work out how many carbons and hydrogens go into that. So 2 carbons is going to be 24 and 5 hydrogens is going to be 29. So that's how you deduce what the structure might be. But taking your molar mass and looking at the functional group, which is technically the heaviest part in this case of the molecule, and then the remainder is going to be 29. So the 29, if we write it in a slightly different colour, highlight it in a slightly different colour like that, that's going to be this part here. Okay, so that brings us to the end of this clip. Sorry it was a little bit longer perhaps than one or two of the others, but there was a few things that needed a bit more explanation. Hopefully it's been fairly useful, and like I said at the start, please make sure that you now take any further questions to subject extensions or contact one of your teachers to help try and clarify it for you. But thank you for listening, thanks for your time, and see you soon. Bye.